All right, so I'm going to share my screen. This is differential equations on March 1st. So we're going to look at what I want you to go into today. And like I said, we're going to go into in modules. I'm going to have you finish up this group work that you were working on, the group work MATLAB project 1. And then we're going to go into chapter 3 and work on this group work MATLAB 2. And so I want to talk more about what this MATLAB 2 project is and what the concept is behind this. And you did and I don't have my notes at home, so this is going to be not real great lecture here, but do just a little introduction to this. You did numerical methods in Calc 2, because not every equation, not every derivative can you find, not every function can you find an integral for. So not every differential equation can I actually solve and get an answer for analytically using the algebra techniques we've been using, or analytical techniques we like to call them, because it's not just algebra we're using. But there are times where we can't do that. And it's funny that I'm actually talking about this today because I just was watching, again, I'd watched it years ago, but I just was watching the movie Hidden Figures a couple nights ago. If you haven't seen it, I highly suggest you go watch it. It's about women back in the 1960s who were hired by NASA to do what we call become computers. Computers in those days were not the actual computers we know today. They were the people who sat there and did the mathematics by hand for to do all the calculations by hand. And so this was the Hidden Figures were about the African American women who worked for the space program and their story, because they're really not seen. Most of the women who worked for NASA in those days were not seen either as computers, but the African American women definitely were not seen. And so this movie is about them and what they went through and the process they went through. And the one was trying to solve sending the Mercury astronauts into space. So when they sent the first Mercury astronaut into space, Al Shepard, he went up and came back down. He just did a parabolic orbit. We just shot him up, parabolic orbit, come back down to Earth, and exactly what we wanted to do. Gus Grissom, the second one, did the exact same thing. But when we went to do John Glenn, we actually wanted to put him in orbit. So he was actually going to orbit around the Earth, and getting him up and putting him in the orbit wasn't so bad. You basically get him into an orbit that will basically, it's an elliptical orbit that goes around the Earth. And basically what it is that you're falling to the Earth and you just miss the Earth every single time. It's basically what happens when you're doing those elliptical orbits. And what they then had to do is change that elliptical orbit into a parabolic orbit so that it would come back down and land on the Earth and not slide off the atmosphere and not burn up in the atmosphere. So they had to figure out how to get the orbit to stop being this nice elliptical orbit into this parabolic orbit. And there's no math that can do that. There's no formula that would actually have that happen. And one of the women, Katherine Johnson, who worked for NASA until she I don't think she's passed away yet. I think she's still alive. She's like 90 something. But she worked for them all the way through shuttle and so forth. And she just got the Congressional Presidential Medal of Honor for the work that she'd done on this. And she realized that there's no mathematical way to actually take an elliptical orbit and make it into a parabolic orbit. And she used Euler's method to figure out how to solve that. So there was an actual application where they were using Euler's method to do exactly this information. So Euler's method is a very useful piece. I'm going to draw a little bit to show you a little bit. And again, you did this in Calc 2. Whether, again, I think you remember it is a different issue. And what we have is, let's say we have some function here that we're trying to solve and find out what the solution is to that equation. And we've got some point here, we'll call it x0. And the x0 comes up and we hit right here. Now this graph is actually the derivative. So this is actually whatever the derivative is that we're working with. Whoops. Didn't mean to do that. Didn't mean to do that. So this is actually a derivative. So let's just say it's y prime. And what we do is what we want to look at is we're trying to find the equation that will solve this. And what we can think of is we can think of having a tangent line that comes along and hits the curve right at that one point. And then we come over a step over a little bit. And we come a distance over, we're going to call it h. So this is plus h. And this gets me to my x1. And we're going to use the x1 here on that derivative and then figure out what this would be. And then we're going to do this again, and we're going to draw a new, at this point, we're going to draw a new tangent line in. I'm just going to draw a line, a new tangent line in, and then you can keep doing this until you can actually get an idea of what that equation would be, what the function would actually look like based off of that. And what we get is we get y1 is equal to y0 plus that slope, which is the derivative, times x minus x0. This is the point slope form. So this is y1 minus y0 is equal to your derivative times x minus x0, derivatives being your slope. So this is basically the derivative, the point slope formula. I'm going to rewrite this a little bit and call this x minus x0 is going to be h. And that gives me my equation. And then xy2 is again that same thing. Point slope form is going to be y1 plus that slope times that h. And we keep doing this process until we find out what this would be, where h is equal to whatever interval you're on. So b minus a. Over top of however many divisions you want to do. So we put it over top of n, where n is just how many times do I do this in here? How many divisions? If I'm going to go from here to here, so here's my b and here's my a, I just decide how many divisions do I want. And so that the number of divisions is what my n would be. And we do this process and we figure out what this is. And we keep this process going, and the better you do, the more divisions you have, the more accurate this answer would be. And then you find out what your nth value would be, whatever the value you want to find. And you're going to keep this process up. And this is why computers are nice, because this is a very tedious process to go through and calculate. And so we do this using computers. And I'm not going to do this example because you're going to do this in the computer, where you're going to have the computer do this for you and calculate this for you and figure out how to do this. And so you're going to see that. And so the next one I want to show you is another method we use called Runge-Kutta. And I spelled Runge wrong here. Sorry about that. It's an E. And Runge-Kutta is another method we use. We're doing the exact same thing. It's better than Euler's method, because Euler's method, you have to do a whole bunch of values to get a bunch of divisions to get a really good answer. This one does it much faster by doing this thing called a weighted average. And again, we're not going to do this ever by hand. I just want you to see what the formula look like. M is the order of your method, M being how many divisions, how many weights you're going to have. So this subscript of M is how many weights you're going to have. You're going to add up all these weighted averages and add up all these functions evaluated at each of these points, and then have all these weights. And this is really obnoxious to do by hand. So this is why we have computers that do this for us. And so you're going to use Matlab to do both of these processes, both the Euler's method, the Runge-Kutta method, and you're going to see how well do they both estimate the answer to a differential equation. So again, what you're going to do here is you're going to finish up the one you're working on, the MATLAB you're working on. Then you're going to go into chapter 3 and work on this group work for MATLAB 2. I've given it to you as Google Docs. I'm hoping these Google Docs are a little bit better shape. This talks about how to do Euler's method, but I'm actually not going to have you program it yourself. I can give you, if you want to learn how to program it, I can give you that information. I'll try to post that today of how to actually do the program if you want to program it yourself. What you're going to do, Euler's method is not in MATLAB. You have to actually program that one yourself. If you go into the home menu and go down to MATLAB programs, Euler's method is in this list. And so all you have to do is copy the Euler's method here, put it into your MATLAB program, call it Euler.m for your Euler method, put it in your MATLAB program, and it will work. If you're at home, which you all are at home, you're going to have to use Octave. Again, Octave is the same. You know what? I don't have Octave ever up on this. So let me go get my Octave. So you can get Octave by going into your modules. There's actually in the start here, there's a MATLAB substitute. So you're going to go into Octave. Octave again looks just like MATLAB, very, very similar. You need to sign on in. I signed in already with Google once, so I'm going to sign in with Google. Get myself signed in. Then this is the command line like we had in MATLAB. You had that same thing. If you want to create a script, you come over here and hit the little plus and say you want to do a script. You then name it. This would be your M name. This would be the Euler.m. This is the name you're going to use for that. You then say, okay, this is what you want to do. I can't do that because I already have a name by that. It would then show up in here. I don't know why this is. So I already have it in here because I've been in here already. Then all you do is copy and paste that information directly in here and then hit the save button. Okay. And then you can run this, and the way you run it, it talks about that in the group work on how to run it and how to work it. Runge-Kutta, it's called the 4th, 5th order. It means that you have 4 or 5, basically 5 or weights that you're going to be working with. It's actually built into MATLAB. It's called ODE 445. And again, it will talk to you about how to go through this. This just gives you what this is look like, and then you actually get to the exercises where you do the exercises. In this case, I just want you to do the exercises directly in here and put your answers in here. And you can do these either together as one group. I will show you what the groups were last time. This is the kind of the groups so you know which one you should be working on. Last time we were in these groups. And so this would be the group you would go into right now, either in the group, either for the MATLAB 1 project, this is the group project you go into, or the MATLAB 2, this is the same groups you're going to go into. And then I just need one person in each group to turn it in, but all of you should be working on it. This all makes sense? You all good? All right, so what I want you to do, whoops, is somebody in the chat? Okay. So
I
what
was wondering, I kind of missed where you got where you copied the script from or the code from.
So let me share that again. Let me share that again. So share my screen just real fast. So on the home page, there's a MATLAB programs link. You go into that MATLAB programs, And there's a whole bunch in here. Some of these we're not actually using this semester. You're going to go down till you find the one that actually says Euler's method. So this one says Euler's method. Here's the name you should give it for the M file. And then here's the actual file. And you just copy that all the way down to the end and copy that and paste it in.
Gotcha.
Okay. And then it talks about how to use the RK method. It talks about that in the notes also. For both RK and Euler's, you have to put in this piece here. You're defining your function, where your function is what y prime is equal to or u prime is equal to. So y prime should equal something, and then you would type that in. Like here, I say y prime is equal to 2y plus 1 over 1 plus x squared. I then type that function in here. I do that same way for both Euler's method and RK. And then here's the notation for RK, what you would do here. And for Euler's, this is actually, it's in the name of the function. That's the command you would use to do the RK. You would just need to put in what your x span is, what your initial value is, and what your n is. And that's how you run both of those. Okay. On RK, it's basically the same thing. You put in your function first, define your function, which we should have already done at this point. You then, and I don't always use the x and y in the group work. It's going to talk to you about not using just x comma y. It might use different names because otherwise you keep overriding itself every single time you do that. So there's different names you can give those. And then it's ODE, and then the function, your t-span, what your a and b would be, and then what your initial value is. Same thing on Euler's. You type Euler, you type the x, y, though I would do something different, which the group work tells you, and then Euler, and then f, and then your x span, whatever that is, your x, y, and your initial value. And this has an n, so you have to put your n value in. Okay. All right, so I'm going to stop recording unless there's other questions.
I have a question real quick.
Yes.
So my group member isn't here today. Am I just going to go ahead and just work on this alone then?
Yeah, and what I'm going to have you do is I'm just going to have you all stay in here so you can all talk to each other. Just work on your group project. Just work on your actual Google Doc. But you can all talk to
Okay.
each other. And I'll stay
Okay.
on. Okay. So I'm going to